Uh, a different one. Can you guys see the reaching definition slide now, Nathan?
Yes. Yes.
The
We can.
iterative algorithm.
Yeah. Yes. We can. It's not in presentation mode. I don't think. But yes. Yes. We can see the. I can see the window. Okay. Yes. This looks great.
Okay. So folks, welcome back. I hope everybody is doing well on the homework one, which is due at the end of the week. And just a couple of announcements going forward. So we'll be giving the next homework, which is a theoretical one, not an implementation oriented, to test the data flow analysis that we have learned. And then in parallel, beginning next week, we'll get started on our first project. So hopefully by doing the first homework, all of you have gotten a good ideas about the data flow analysis, and also LLVM infrastructure, more importantly. And we should be ready to get started on the project. The project will be done in terms of teams of 2 students per team. So I don't know if we have even number of students in the class or not. And if not, we'll allow one team of 3 students. Or if somebody wants to go solo, we can just have 2 students per team and then a solo person. But please look for your teammate. You can use the Piazza teaming feature and get the teaming done. We are going to do 2 projects. Hopefully we'll have the same team for both. And the nature of the project will be to implement some kind of a state of the art paper in LLVM, which is not implemented correctly currently. You'll have to understand the SSAIR. Of course, we'll be learning about how to generate it and so on, but of course you don't have to generate it, you just have to use it and then take the paper and implement it in that IR. So start familiarizing yourself with the IR. It's a good bit of documentation there. It is similar to quads, triads, except that we have at each join point we have a new definition. When multiple definitions merge there, we have a phi function. We generate a new definition there, and that definition then persists for the remaining part of it and things like that. And we'll put some stuff on the SSAIR, but there is a good bit of LLVM documentation available there as well. So those are the 2 announcements. First is about the homework, which is theoretical. Second, which is about start teaming, and let's get started on the project. Part 1 and 2 are independent. So, but we'll go ahead and give details next week. So going forward, we will touching the topics on this data flow analysis for reaching definitions, and One of the things that you notice here is, of course, we are monotonically growing these sets, and we are converging when there is no more change in the set. And the second aspect of iterative data flow analysis that we looked at was that we must start it at the when in functions in sets are phi, and we keep going them, and when they don't grow anymore, we stop, and that gives us the precision of generating the minimal set of reaching definitions under the data flow constraints which reach a given point. We could satisfy these constraints. So data flow equations are, as you can see here, they're nothing but constraints. And with respect to the seed of the solution and the algorithm, the constraints will be met at convergence. So, and there could be multiple solutions to data flow equations. And of course, the interest in terms of precision is we want to find the minimal one for reaching definition analysis. Because of course our goal is, if we find that certain definitions are reaching a given program point, then we want to use their properties and do certain optimizations, such as constant propagation and so on. So if we, for example, find two definitions are reaching, in this particular case, at entrance of the basic block B4, such as D6 and D3, using the properties of those two, if they're bound to same constant, we could do certain change to the program by rewriting the reference to A by the constant. So that being the case, our goal is to find out the minimal set which is satisfied by these sets of equations, and that's why that initialization, which I'm emphasizing again and again. And the second aspect of this is, as we talked last time, which is about safety and precision. So we are introducing approximations in this analysis because we don't have the precise information at compile time, such as what are the feasible paths, what are infeasible paths. That's one thing which we looked at. And since we don't know that, we must assume every path is feasible. And in this example, I think I explained it one time that if we could have a B1 to B2 to B4 as a feasible path, then we of course have a reaching definition D3 going to B4. If that's not feasible, in other words, we must go through the loop at least once, if that's the way the loop is written, then obviously the only definition which reaches B4 is D6 and not D3. And that makes a big difference, because if you know feasible paths, and we can be more precise in the absence of this information at compile time, we must assume all paths are feasible, and therefore we go by the simply by the edge propagation in terms of algorithm, and we propagate, for example, D3 to B2, and then B2 doesn't kill it, so it gets propagated further, and we assume that, of course, dynamically this particular execution condition may realize, and therefore D3 may reach the B4. So that is one approximation on the paths that we assume. I mentioned that while developing the control flow graph itself, we must assume all possible edges which we could encounter And in this particular, of course, generation of control flow graphs, we do have the labels and other things available to the compiler to precisely determine where we branch and so on. So in that sense, we know that the edges here are precise. But if we have to generate a control flow graph from our lower level representation, such as binary code, assembly, etc., then we may have a branch there which is based on the label, and that label may be something in terms of a register indirect branch, and we don't know what it is value at compile time, and therefore we must assume it could go anywhere. And if we do not, and if the branch somehow goes to a particular program point, what will happen is it would have brought a particular definition along with it, and since we do not have that edge, we have ignored that definition, and it will not result in the correct modified program, because here we have ignored a particular definition which could reach a given point at runtime during some execution, and we didn't account for it in our analysis. We didn't find it to be reaching because there was no control path along which it could have gone. We ignored that control path, and because of that, the set of definitions that are found and used by the analysis is not really a super set of the actuality, and because of this reason, the program semantics will change. So in other words, safety condition for this analysis is it must find a superset of the actual set of definitions, and the approximation that we introduce must preserve this condition. So two approximations. One is the set of edges that we include in the control flow graph generation must be over approximation. Secondly, we assume all paths are feasible in terms of the control flow, and that takes care of at least the control side of it. Now, as I was mentioning in the last lecture, that doesn't, however, satisfy the real world requirements, and we need to account for that, and that's what we need to we'll focus on initially, and then we'll move on to other problems. So what is that real world stuff? Basically, the issue of pointers being aligned with the or pointing to certain variables. So given a pointer, for example, pointing to some variable called I here, which is declared in the analysis, which is used. And imagine a dereference on that pointer. Now let's first carefully isolate those dereferences which matter and the ones which don't matter for this analysis. So as you know, we are really focusing on here the L values of all the variables that are participating. We have shown here in the graph even some R values, but those are not really important. For the purposes of analysis, we are just using L values that, hey, this particular definition starts here, it goes around like this, and it reaches there. And therefore, this L value of this particular pointer dereference is really important. So for example, if you have star P on the left-hand side, star P equal to something, where star P is a dereference to a pointer, that's the one which to worry about. If you have a star P or a R value use of a pointer, that doesn't change anything as far as reaching definition analysis is concerned. So we'll leave that alone. Now, star P on the left-hand side, how to interpret that is really an issue. And so if we knew statically that star P really always evaluates to, let's say, assignment to I, because P always points at that point to the variable I. If we knew that for sure, how will we know that? It will be something like P is equal to ampersand I, or P is set to the address of I just before this point. That will be a case where we will for sure know that P points to I at that point. Star P there, then it's an easy interpretation. because what it is doing is P is set to point to I. P is dereferenced, and to star P is equal to something. And effectively what you have here is a definition introduced there through an indirect name, like I equal to something. So we'll immediately substitute that reference by I equal to something, and we will generate that definition, and all of the analysis will be just fine if that is the case. Now that's a very, very special case of what really happens. Many times we would not know statically where the pointer is pointing to, and there could be multiple cases here. The other case would be that maybe it points to two objects. We know that also precisely, that pointer P points to A or points to B. But at a given point, depending on how we have come through the predecessor control flow block, basic block, it may point to A in one case, it may point to B in another case. So we are not really sure. But we could say that, okay, it points to either A or B, and then take some decisions accordingly using this. This is also a very special case. And the most important and more common case, unfortunately, is this, that we just don't know where the pointer points to at static time. Just like we don't know whether the path is feasible or it's not, we just don't know anything about the pointer, and therefore we may have to just assume that it points to any of these objects which are sitting here, which could be I or J or A or whatever is being analyzed. And that becomes a very deadly case. Now you may say, oh, let's do some analysis and decide on where the pointer points to. The problem is this, that pointers in languages like C, C++, they are independent entities. They are not really object references. So in general, if due to pointer arithmetic, such as P being incremented, decremented, or even even some multiplications, etc., on pointer could occur. And we don't know by what amount the pointer is incremented or decremented, and where it would sit during the execution. And therefore, statically, it is impossible to analyze a pointer given the pointer arithmetic's presence in languages like C, C++. Java pointers are very different. They are object references. They will get confined to a given object. And so the analysis there is pretty clear that the Java's pointer tells us that, here is the object which is being dereferenced as L value, etc. And we will be able to figure out, just like in the first example, P is equal to ampersand A. That is an example of a reference to an object A. And using that, we will be able to find out which object is being modified here on the L value side. But C, C++ pointers do not fall in that category. And unfortunately, while the pointers have a lot of power, it introduces a lot of problems for the pointers. So in short, the most general case at compile time is that the pointers are not analyzable, and we got to assume that they could point to any of these different objects or variables in the analysis units. So the question is, how do we interpret them in light of safety? Given this limitation, how do we go about interpreting them? As I said, if we have a very clear case, like P is equal to ampersand A or an object reference in terms of Java, that's an easy case because what we will do is we'll simply substitute that star P by the I is equal to such and such if P were to be pointing to I, and then run the analysis, because it will definitely introduce a definition of I at that particular point. But when P may or may not point to a particular I or J at a given point, then what do we need to assume, and what is its implication? So let's assume that we just take a simple-minded approach and decide to just ignore those pointers. Will that result in safe condition, safe generation of data flow facts? And of course, if you look at that, then we would have ignored if potentially the pointer is pointing to some object A, and we have just removed that star P, and that would have generated a definition of A at that particular point. What we have done is we have taken out certain definitions of A effectively from the IR, and that is going to lead to a problem because the definition of A would have gone down from that basic block. It would have reached somewhere, and if that is the value of A which is reaching at a given point which you have ignored effectively, then let's say you did some optimization like a constant propagation. All other definitions of A that you included were all constant except this one, and you ignored this one because of you deleted the pointer, and therefore a non-constant value was reaching there, which you substituted by a constant value, and that's unsafe. So, so in short, you simply cannot eliminate that definition. So what it means is what set here specifically we need to modify out of, we have two basic sets here. One is gen set and one is skill set. So the question is, given this, what I just said, that we cannot ignore a definition, which set should we modify first and how? Anybody has about that? And we don't know where the pointer is pointing to. So we got to kind of make an assumption and then modify at that particular point. Star P is equal to something was sitting in the IR for running the data for analysis. We should do something to the star P. I of course showed you that if you just remove it from IR, you're creating an unsafe problem here. So the question is which set we should modify and how. And we don't know where P is pointing to. Anybody has any suggestions? I hope all of you understood the problem. What we have is in the IR, we have a star P equal to something sitting somewhere. And we don't know where the problem, where the pointer is pointing to precisely at static time, because, and we can run all kinds of pointer because the pointer can be manipulated using arithmetic, addition, decrement. It's possible that it could go to any object or any of the variables and alias with that. And so therefore star P, we cannot simply say it is confined to an object A or scalar variable A or B or C or like that. So what do we do with the star P, and which set do we modify and how? Any answers? You can raise your hand and maybe I think Nathan can ask.
Sorry, my internet was coming in and out a little bit. But what did you ask me?
No, I asked them a question that star P is equal to set at L value, and we don't know where the P is pointing to because of limitations on static analysis. And so to reflect this properly into the reaching definitions, which set do we modify here and how?
And I'm sorry, you wanted me to check for answers on that on chat, or you wanted me to try and answer?
No, not you.
Okay.
Just pick somebody who is on the chat.
There's no one on chat right now.
Anybody wants to volunteer? Just any answer is same. It's fine.
Can you start with the gen set? Modifying the gen set, we can assume that the pointer, it can point to any variable present. So we can consider that to be a special variable and add it in the gen set whenever there is an L value like star P equal to that. Can we do like that?
Excellent. Yeah, that's what we have to do. Because what would happen is, think it in this particular way, that what is this genset reflecting? It is reflecting a definition which is starting at that point, and from there it will flow everywhere, and so on. And imagine a situation at runtime where pointer p is alias to some variable, and because of that, the definition of that variable will get generated, which is not really seen in a transparent way in the IR, and that's the one which we should include. Now, of course, it could be any variable. So maybe at point some execution, it could be I, some other execution, it could be J, third execution, it could be A, and so on. So it could be any one of these variables. And so we must include the definitions of all the variables which start at that particular star P by adding them to the genset for the corresponding basic block. You can see what an havoc this will play on data flow analysis, because now all these suddenly so many of these definitions are going to start off from there, and some of them will probably reach a given point and it would kill the analysis. And that is one of the reasons why the cease pointers, although they are very user friendly, they're a big detriment to the data flow analysis because of the unanalyzability they introduced, because they can go anywhere and point anywhere as per the C semantics. They are also untyped, so it is very difficult many times to really use typing to restrict that, hey, maybe this pointer is integer type, so it cannot go to a float, and so I can safely rule out at least those variables at this point, because it's casting and all kinds of different issues there, which leads to type analysis being extremely limited. So that's about the genset. So the genset must be expanded. Are we done, or is there something else? What is the impact now that we have introduced star P at a given point? And you can see here we had two sets here, gen and kill. So any impact on the kill set, and what is that, especially under this condition? That's the second thing that we need to worry about. Anybody from volunteering to answer that? So again, the question is this, that we accounted for by generating all these definitions at star P equal to such and such point, and we generated a new gen set which has all those definitions, and then we rerun the data flow analysis. But as we know, the moment we introduce a definition, like for example, there is D4, which is I is equal to such and such, and that has an effect of, if you go back in our slides, the way we had analyzed these was, of course, we had a gen set, but to even begin the analysis, we had, remember we had set up, there is another set, which is the kill set for that particular basic block. So because now you introduce all these definitions, what will happen to the kill set? What is the correct interpretation here that we must use in order to make sure the analysis is still safe? I hope the question is clear. In things like, because we have a definition point, now we would have introduced one because of star P, right? Which wasn't originally there, let's say. We introduced that. Now, if we do it the same way here, it will have an implication on the kill set, the way we generated this kill set. Should it stay change? And what is the right thing to do between these two alternatives? That's the question. Any volunteers?
So when we defined the kill set, we said that the all definitions can reach anywhere. We ignored the path. So in the same, by the same logic, all the new definitions we included based on the pointed thing, can we add that in the kill set? Assuming that because of the negative operator, it would not be in the inset. So all the definitions, can we add that? Whatever the new definitions in the gen set, we can add that the same thing in the kill set.
So all the new definitions can potentially reach the inset of that block. That is true. Okay. The question is, if we follow the same way of generating the kill set, right? Remember how we did it? Like in this particular case, the generation of kill set for B2, we took all the definitions for I, and then we took out from there everything was gen, right? And all of those were put in the kill set. That's how we generated the kill set. So if you follow the same procedure for the introduced definition, is there a problem here, or is that going to be okay? Or in the presence of pointers, will the kill set generation change or will remain the same as it was for in the absence of pointers? And why? It's fine to just give some answers. Thanks, Bodhi, for volunteering. Anybody else? Or Bodhi, you can also give, that's not a problem. I hope the question is clear. If not clear, please raise your hand and ask. I mean, I don't like to teach the class remotely, but you know, I have a condition which I cannot really come and teach it in person. So trying to make it as interactive. Think of what will happen, right, on the generated sets. That's the way to think about the implication. So let's say you introduce here star P and you introduce a new definition of I there. Okay, and generated set is now has a new definition of I. Now, because of this new definition of I, and you generated a kill set now based on this I, which wasn't present earlier in the gen set, and you killed all the incoming definitions of I there, right? If that is the way you approach the problem, then what will happen is during every execution, we are assuming here, okay, during every execution, I want to stress this, that we are assuming here that the definition of I sitting there all the time, which is going to kill everything that is coming in. That's the implication. What if P doesn't point to I? Because we don't know whether the P points to I or not. It's not a must condition. It's a may condition. So during some execution, P may point to I. During certain others, P may not point to I. So think of a definition which is coming in, and you assume that every time it comes in, it is killed because P always points to I at that point. That definition is not allowed to go through the block. But what if in some execution or executions, P does not point to I? Because we made an assumption that P may point to I. So it means there might exist some dynamic executions in which P may not point to I. And if the definition of some I comes in at that particular point, and P is not pointing to I, that definition will not get affected. The value in I will remain what it is, and it will flow down. And that basically means that you would have limited a definition again, which would have been reaching a given point when it should not be limited. That you have killed a definition when you should not have killed it because P was not even pointing to I.
So if I understand this correctly, is the implication that like assigning through a pointer, like you can't assume that it kills anything, like because like if you were to assume like the assigning through the pointer kills the value of I, then it's safe to like reuse the memory address of I. But if the pointer actually pointed somewhere else, that would be incorrect.
Exactly. Because if you somehow assume that the incoming definition is kill, and if there is a dynamic execution under which it is not kill, then you would have made an error here, and you would have stopped that definition at this block, not allowed it to proceed. And by symmetric argument about every variable, we can say that although it might generate the new definitions for each one of them for safety reasons, it will not kill any one of them. So in short, the kill set computation here, whatever we computed earlier based on by ignoring the pointer, is where it should stay. We will not enlarge the kill set. Okay. So the answer to this is we will enlarge the gen set as by adding the new definition points for each one of the variables. But as far as the kill set is concerned, we cannot enlarge it, because if we add an obstruction to some definition and that obstruction simply doesn't some dynamic execution, then that definition should be allowed to pass through, and therefore we should not increase the kill set. So the kill set computation will proceed based on the original scalar definition points, which are shown here. And even if we have a star p anywhere in between at any basic block, it will simply not change. Okay, it will not increase unless we know that the pointer is exactly pointing precisely to that variable at that point all the time. Like for example, p is equal to ampersand I means that it is definitely pointing to I, and therefore I can assume that yes, if it's a star p after this point where this condition is true, it is definitely going to kill the variables, the definitions of I which are coming in. So only in that situation is when we can dilate it. All other conditions where we make a condition, even if it's enumerable to multiple variables, and if we are not sure if it is precisely exactly equal to 1, we simply cannot dilate it, and therefore we simply leave it the way it is as computed on based on scalars. So the implication of pointers is pretty scary. It introduces all kinds of new definition points in the presence of May information. The presence of May information, which is a very likely case, which is always mostly true in C programs. It also leads to all the definitions which are incoming going through that basic block because we are not dilating the kill set. And as a result, the analysis results in tremendous number of reaching definitions at any given program point at the end of the analysis, introducing a huge amount of over approximation. If you really oracularly find out which is the set of definitions, if you had some way of running the program for all kinds of input possibilities and record it, what are the reaching definitions here, and that's a complete set, you will see that with regard to this set, the one which is computed by the data flow analysis here will be extremely large. And because of that reason, the analysis becomes very ineffective. So what's to do here? Well, there's not much you can do because of the pointers. Again, because of typing, you cannot resolve it. You can do some kind of pointer analysis. You can determine where they are pointing to, etc. And you can at least get rid of some of the possibilities in some special case, like p is equal to ampersand on one side and p is equal to ampersand b on the other side of the control flow, things like that. But that's about all. All the pointers are used heavily through arithmetic or through linked lists and all kinds of things, and their values are completely unknown, and you cannot reason about them doing the arithmetic, etc. And so that's why C programs are particularly notorious in terms of this data flow analysis. Now, same is the reason I think some of you might have done, of course, 40-40 style class. Remember one question that I always used to ask in the class is, if we have infinite number of registers, is it always safe to keep all the values in those registers? Can we just leave them and operate on them? Again, the answer to that question is no, because the moment you have an alias variable like this, whose alias is unknown, you have to assume that maybe that dereference will simply go and modify the value in the memory. And so if you decide to keep it and run it in the register which is named after I, let's say, you're going to have a problem because the value in the register will be stale, whereas the pointer in the original program would have actually gone and modified the value of I in the stack, and you will basically be having a wrong program generated through a register assignment. So this pointer kills register allocation as well, and those are the two problems which are most deadly because of the problem pointers. And since, of course, the original definitions of C, C++, programming languages and compilers folks have really worked on pointers and getting their semantics under control, and that's why you see object references. And due to data flow analysis and other register allocation becoming better, what you see here is the effect of code quality. Although the pointers are not as effective for programming, maybe sometimes for compiler analysis purposes, they are quite effective. And so that's why the code quality of Java caught up very significantly, very quickly because of these reasons. So that's basically the second part. Now, I just want to quickly touch base on this data flow analysis for the constructs, and then we'll jump into another data flow problem, which is available expressions. So this is rarely used these days, but in olden days, you could do even, because the graph structure is not a general graph, but generated for a given if then else or while. You could generate the data flow analysis by knowing the structure, by catering to the structure. How would you do that? For composing, for example, the gen sets, it's pretty clear that you would have everything that definition kill at that particular point. Here's a set of definitions of D of A minus D, which is what we've seen. And you would generate this for each statement, and then you would off. Like, for example, here, as shown in the second one, the gen sets are composed in this particular way. So it's a very interesting way to think about it. Gen of S, which is a compound statement of S1 followed by S2, is whatever is generated in S2 is always there, of course, because it's downward exposed. But whatever is generated in S1 and whatever is not killed in S2 makes it to the end of S. And so you can see the second part of set is modified. And whereas if you see the kill set, that's also interesting in the way it is composed. Whatever is killed in S2 is of course killed union whatever is killed in S1 minus gen in S2. So if something is not regenerated but is killed in S1, that also makes it into the kill set. So I encourage you to kind of just quickly go through this. For example, if you have if then else branch, how do the gen and kill sets get affected for the special graph? You can see that either one of those gen sets get unionized here, but the kill set is intersected. In other words, something is killed in this compound S statement only if it is killed on both sides of the branch. Things like that. So by looking at the kind of data flow analysis that we have at hand, by looking at the structure, we can generate these equations, and then they can work for particular forms of things which come into being. And as you know, we have typically all the control flow graphs are generated using some programming structures or constructs like these. And so we could generate for a given language a data flow analyzer by just doing these kind of compositions and then just run the analysis using that. That's the goal, and this is called as a structural data flow analysis as against the control flow oriented one. I'll leave some of this for you to study offline. It's pretty straightforward to see what is going on here. So let's shift our attention to another problem now, which is really important. We have looked at the reaching definitions, and what we want to do next is be able to use this information. One of the uses of this information is tying the definition to its uses and trying to find out what can be done using it. For example, if we know that given statement Sn here, Sn dash, is bound to a constant, that V there is equal to a constant at the top of the graph here. Then based on the fact that we have a constant here, we want to see if we can eliminate this constant in wherever this definition reaches. So we have two here. Sn dash is reaching at S1 and Sk. And what we do in this particular case is we, based on the definition, after the sets are found in terms of reaching definitions, we bind this definition point, we put a chain between the definition point and wherever the definition is reaching and is used. So you will see that these two chains are built here. Okay, it will take some time to, of course, build these chains. I mean, some effort. But by following this, we quickly are able to go to the uses of a given definition, in short. And we find out if that should be changed to a constant. Why do we do this? Because, again, we have very few places where there are constant definitions. So if we run then, after we run the analysis, we start with the definition points where there are constants. We chase these DU chain to the places where they are used, and then we make a decision. Now, how do we make a decision? We make a decision based on what is going on at the use point. If this is the only definition which is reaching, let's say Sk, then we are done. Then we simply substitute this V into that V over there, and the use as a constant, and we are done. But if we are not, then we need to worry about a different thing. What are the other definitions which are, and for that matter, we need to worry about UD chains. So here is the case where, let's say we were at a particular place where we found one of the nice constant definitions reaching, but we need to find out what are the other definitions now which are reaching. So we build a reverse relation here from those uses and bind those to all the definitions which are reaching. So we know the set of definitions which are reaching a given point. We simply connect all those definition points to this use point, and that's called as a UD chain. So we reflect back here, we find out if all those definitions are constants. If they are not, of course, we reject the propagation of constants. And however, if they are, then we just substitute it. And this navigation, once we do the reaching definition analysis, this UD and DU chains allow us to very quickly navigate the IR with regard to certain optimizations in terms of what to do. Now, one of the uses of course, this reaching definition, as I pointed out, is in terms of constant propagation. The other use is what is called as a copy propagation. So let's say that we have a definition which is A is equal to B, and we have another reaching definition which is bound here. So let's say that this is A is equal to B, S1 dash is A is equal, and SM dash is also A is equal to B. And therefore we have these two definitions reaching here to the use of this A. This V is the A here. And so the question is, we would like to substitute this A by B by taking the copy. Now you may ask me why we need to do this. Well, the big reason is this, that many times lots of copies are generated in the program, in the IR. They carry the same value through different names at a given point. And for the purposes of register allocation, you want to reduce the namespace. Instead of saying that both A and B, and we could try to give registers to both A and B, we'll simply substitute A by B. So we'll have reduced, gotten rid of A as a namespace here. And therefore, we'll have only B to be kept in the registers. Otherwise, we'll have to give two registers, one for A and second for B. B is already being used. Remember, S1 dash is A is equal to B. So B is already used there. SM dash is the same way. So you have already for holding B in a register. But if you eliminate A and just put B over here, we'll be allocating register only to B. So to reduce the namespace here like this is one big reason for doing the copy propagation. So you may ask me, where do these copies get generated? They do get generated a lot because of the kind of IR you begin with. One common reason they get generated is by call by value semantics, wherein all the arguments are sent as copies to the across the calls. That's where they get generated. They carry those same values and then end up using those. The second is because of all kinds of optimizations, including elimination of expression, CAC, things like that. And the third reason, most important reason, is because of the IR, which is lowered further for register allocation. So for example, in SSA IR, when you have a fee point, on left and right side of this, if you have two different definitions being merged through a fee node, the fee node is, of course, a selector between A1 and A2, and A3 is generated as a copy of either A1 or of A2. And because of that reason, you get a lot of copies generated and propagated. So to get rid of, again, the namespace here of A1, A2, A3 like that, and which will unnecessarily introduce register copies, etc. The IR is sent back in the original non-SSA way, and these copies are then purged. So in other words, the same analysis yields you which are the reaching definitions. The question is this, though, that if you have A is equal to B in S1 dash and if you have A is equal to B in SM dash, is it okay to simply get rid of A from SN and substitute it by B? We did this for constants. Is this safe for copies? That's the question. Anybody? So if we have A is equal to 10 and A is equal to 10 in those two statements at the top, we would have substituted A by 10. Now we have A is equal to B and A is equal to B. And we want to change the bottom to by A by B. Is it safe? It's okay to have a wrong answer. Don't worry, guys.
Is the value of B same in both the definitions?
And they could be different.
So in that case, if you replace, then depending on what path, what definition reaches at the end, so then we cannot replace, right? Because if the value of B is different.
So let's for now assume that A is equal to B in S1 dash. B is carrying a different value over there. Okay, and SM dash the same way. The value of B that is seen over there is different. Let's call them B1 and B2 for some clarity. But what will happen in the original semantics of the program is A will get B1 on the left hand side and deliver A there, B1 there at the bottom, correct, through the name of B. And same thing will happen on the right hand side. The delivery, of course, will be of a different value, but again through the same name of B. And so if we simply get rid of A by B, B will mean B1 on left hand side and B will mean B2 on the right hand side. So it will still be safe, even though the values of B which are participating in S1 dash and SM dash are two different ones. So what's the catch? Obviously it is unsafe, otherwise I will not be asking this question, but not for this particular example. It's for this example that you pointed out, it will still be safe. Come on, anybody else or Bodhi? So now look at it very carefully in terms of what is the reaching definition analysis really showing you. It is simply telling you that this is the definition of A which is reaching here. This is the definition of A which is reaching here. But imagine now, this is the answer, of course. In between S1 dash and Sn on that path which is shown by the jagged line, somehow A has not changed because of course it's reaching, so it is finding its way there and delivering the value, and it's the only reaching definition from coming from there. But along that path, what is the guarantee that B has? We haven't accounted for that in the reaching definition analysis, so B could have changed. So the relationship of B's value, which is staying in coming through A here, which is the old value, is not maintained if we simply substitute the definition of the A by B here, if B were to be reassigned along S1 dash to Sn. Because what would happen is, imagine this, at the top level S1 dash, A has gotten the value of B1, which was present there. Subsequently, the value of B changed from B1 to B5 on the jagged path. Okay, so now if you examine the value of at Sn of what is A, it is still B1, whereas if you examine the value of B here, it is B5. So if you substitute A by B, you will be violating the program semantics, because you will be bringing the value B5 there, which is regenerated along that path, which is put into B along that path, and that's why it's creating a problem. So in short, reaching definition analysis is not immediately safe for copy propagation. What is the condition here? The condition here is after that particular definition is generated or copy is generated, along no path we should have a change to B. If we have a change to B along any path, and if that path is somehow taken like this, I mentioned, B5, we'll immediately bind a different value along that path to B, and therefore the substitution of A by B, which is B1, intended one, will be wrong. So then how do you account, or how do you use reaching definition analysis for copy propagation? You have to make sure this condition is checked. How do you check it? You go along this UD chains along from the use side to each of the definition side, and you enumerate all the paths that are there from U to D, and you make sure you have no change to the copied value. If there is along any path, if you see there is any change, then you have a problem and you cannot use this for copy propagation. Is that clear? Why is the case? Simply like this, A is equal to B is set at the top. Somewhere along the road, okay, B is changed. And therefore, if you substitute B at Sn, that's the new value which you are bringing in, not the old one which was in A. And your intention, of course, original program was to bring in old A. So to ascertain this, if you want to adopt this analysis, then you got to check this condition along all the backward paths from each U to each D, and make sure that the copies values is not changed. So then this means that after doing the analysis also, sometimes there is further analysis needed to be able to use it in certain cases. And this is one classic example of reaching definition analysis being not directly useful for the copy propagation. It is directly useful for constant because constants cannot be reassigned. They are manifest values. They are not reassignable. So that's why no changes will be allowed on constants. It's safe for constant. It's not safe for copies. So that sets the stage of what is the other stuff that we need to do in terms of either a separate analysis and which captures this condition directly, and that analysis which captures this assignment operator and many other operators of resulting expressions. Here is an expression which is really resulting here through an assignment operator. A is equal to B. That plus all the other generation of R values of this X plus Y kind of stuff, that is called as available expression analysis. And let's introduce that and then we'll see. So in short, to do the copy propagation, we'll have to do some extra work on top of reaching definitions. So then that means that can we have an analysis which is unifying this and copy propagation and X plus Y or X star Y kind of thing. So this is defined as availability of an expression, including an assignment expression. Assignment is a special case of an expression. So available expression captures this type of condition and is one of the most foundational analysis which is used for data flow purposes because it leads to a lot of redundancy elimination, the use and also copies getting sort of eliminated. So what is it about? It's all its purpose is to tell us if the expression is available at a given program point. So here is again a clean definition using paths, and then we'll break it down again using the program points and basic block oriented propagation of values. So what it really says in the very original form is that from start node to program point P, we must evaluate x plus y. Okay, so if there is some path along which it is not evaluated, then it is not available. That means we must encounter evaluation of this along all paths. And then the other condition is this, which is pretty straightforward and simple to understand. So after the last evaluation of this particular x plus y, and prior to reaching P, we do not have any assignments to x or to y. What that means is the expression is intact in terms of its value, because the moment you assign to x or to y, and if you were to reevaluate at it x plus y at P, then the value of x plus y at P will be different than the last point of evaluation. And to preclude that, we do not have any reassignment to x or to y after this last assignment or last evaluation of x plus y. So together these conditions tell us that an expression is available at a given program point. It's pretty intuitive to see this. What has really happened is this, that before coming to this P, no matter which path we by, we always evaluated x plus y there. Okay. And after that evaluation took place, again, we have multiple paths to come to P. Along every path, we have no reassignment to either x or nor y. That basically means that if we see the value of this x plus y at the last evaluation point and at P, they're exactly identical. This is true across the board. Now, if we have multiple evaluation points, they themselves might differ in terms of what values of x plus y they generate. That's not the point. The point is this, that between the last evaluation of x plus y and the value at P, they must be identical. So again, in this particular case, if you apply this condition to your copy propagation, it's going to be true. How? So in this particular case of copy propagation, right over here, A is equal to B is assigned here. So that's the evaluation point. A is equal to B is assigned here. These two B's that participate in S1 dash and SM dash, they will be different. They need not be the same. They are different. But what we are talking about here is after this assignment, there is no change in A and nor there is change in B, which guarantees that S1 dash and SN have the same A's and B's participating. And similarly, SM dash and SN again have the same A's and B's participating here. And that's what matters. Because if we substitute this A by this B, then in first case, it will be B1. In the second case, it will be B2, and that will be consistent with the program semantics. So after the last assignment point, there is no change to either one of the X or Y's. That's the important condition for availability of an expression. And that really helps us to get rid of redundancy and so on. So let us look at certain examples here of what is going on. So we have an expression here, A star B plus C, A star B plus C, whatever, C is reassigned here and so on. And the question is, of course, is the A star B available at the beginning of B4? So you can see here let's apply the path condition that they must be evaluated on every path. So this is evaluated, of course, on this path here. It's evaluated on this path here. So that condition is met. Second condition is after the last evaluation point, neither A or nor B should change. That condition is also true, and therefore, as far as A star B is concerned, it is available. And so what can we do about this in terms of optimization? We can try to do something with it. And you can see that A star B is also evaluated again here. And we already have the correct value of A star B, whatever that is in S1. And that is the same as this A star B in S4. Similarly, in S2, whatever A star B is the same as A star B in S4. And so we can just generate the expression here, evaluate it once, assign that to X, assign that to Y, and whatever is that value, we can just take it and use it here. And that's how we can avoid recomputation of this A star B in B4. And that is exactly what is done here. And we generate A star B in temp, and we generate that plus C and assign it to X. And do the same here. We can then take this temp and just directly use over here, and we have avoided the computation of A star B over here. Now, so in order for an expression to be eliminated at a given program point, first of all, it must be available there. And if it is available and if it is reevaluated, then we can get rid of it. Is transformation. We must introduce here some temporary, which is a unique name, which doesn't clash with anything else, not to disturb the data flow. You may ask then that, hey, why don't we just do A star B plus C, the whole of it, and eliminate it over here? The question is, can we do it? So in terms of, let us find out if it is available here. In terms of availability, first of all, on all paths, it must be evaluated. And after the evaluation, none of the operands should be reassigned. So the evaluation condition is met here, that on all paths it is evaluated. But on the right-hand side, you can see one of the operands, C, is reassigned here, and that makes this unavailable here. And because of that reason, we cannot really do this optimization on A star B plus C because of C's reassignment on this path. So how do we run this analysis? How do we try to find out the available expressions? And so first of all, we can use it for finding out, as I said, copies as well, and these type of expressions also, like A star B. And the analysis itself is not very difficult. You can see a lot of similarity between this analysis and reaching definitions. So really speaking, I'll just introduce it quickly and then we'll worry about it next time. So what we do is, when a expression is evaluated, if it is downward exposed, we note that it is available till the end of this block, because we have made that condition from that program point onwards that it is evaluated and its operands haven't changed. That is, A and B have not changed between S1 to the end of this block. We'll make this available here at the end of the block, such expressions whose operands haven't changed and which have been evaluated, and which we call as downward exposed expressions. We'll include them just like downward exposed reaching definitions, and we'll put them in the gen sets. Now is the question of propagation across basic blocks. So you can see that this criterion, after the last assignment, there are no subsequent assignments. That is one criterion. The second one is In order for some expression available at a given basic block, it must be available on each path leading to that P, which basically means the operator for joining the availability at B4 must be what? It must be intersection. And that's the only difference between reaching definitions and this analysis. In order for A star B to be available here, it should be available at S1 and it should be available at B2. And on both sides of the path, that means the operator at B4 is intersection. So out of a given basic, the inset, the way it is computed here, will be using intersection as against the union. Now, in terms of killing an expression within a particular block or across block, it is exactly the same. If one of the operands is redefined, that expression, even though it may be available at the beginning of the block, is no longer available. For example, A star B plus C is available at the beginning of B3. However, because of redefinition of an operand, is no longer available at the end. So that kill set is the same and is found using the redefinition of an operand. Those are all same. Gens are the same. The only difference is the intersection at the beginning of a basic block rather than union. And that defines the analysis in the same way as a similar way to reaching definition. So we'll stop here for today. And we'll take, of course, the questions if you have any on the your office hours. And see you next time. We'll wrap up the data flow analysis. We are almost towards the end of basic data flow, except for a couple of things remaining. And then we'll look at a little bit more advanced data flows, the uses of these data flows, and then how those uses were sort of subsumed by more advanced analysis like PRE. So just to give you a heads up, what is coming up is how is reaching definition analysis useful, where it is used and where it is not useful, because it doesn't capture some key condition like for loop invariant code motion. And that analysis, which is called as dependent expressions, which capture loop invariant code motion, and also the case here. See, the A star B plus C is partially redundant. So if, for example, if we come from the left-hand side, B1 through B4, we would have eliminated it, but not on the right-hand side. So what do? That is handled by this modification, which is called as partial redundancy of availability. And that leads to the advanced data flow in the non-SSA. And then we'll shift to SSA-based analysis. Thank you and see you in the office hours.